Welcome back. Last time, we started talking about the concept of correlation, which describes the relationship between two variables. For example, this past weekend, I did a 67-mile bike ride, a bit over 100 kilometers, and it included some really big hills. So I could ask the question, is there a relationship between the steepness of the road, or the gradient, and how fast I was going? Now, I can tell you from my own experience that there certainly was. As I was climbing some of the hills, I was barely moving, and when I was going downhill, I was flying along pretty well. Now, last time, we noted that when we have two variables, we can put them together and consider the relationship between them. And so is there a positive relationship such that as one increases, the other increases? Is there a negative relationship such that as one goes up, the other goes down, or no real relationship between those? In this graph here, we see a pretty strong negative correlation such that speed goes down as the distance climbed goes up. So that's the direction of things. We also talked about the strength of the relationship. In order to quantify what this strength is, we use what's called the correlation coefficient, or R, to describe the relationship between the two variables. R is a statistic. It's created by Pearson, and it ranges from -1 to +1. Values closer to 0 are considered a very small or non-existent correlation, and as we get closer to either -1 or +1, it's a stronger correlation. So that's what we covered last time, but the question is, how do you actually calculate that R statistic? And that's what we're going to talk about today. This is a bit mathy, so I know that can be challenging, but try to get the conceptual idea of where these numbers come from. I'll note that there are several different ways to calculate correlations. I'm going to note 2 of them. There are a few others as well. Use whichever one makes the most sense to you in your mind. Let's look at the first way to think about how we calculate the correlation between two variables. When we talked about a single variable, this is going back to when we were describing data, we could describe things such as the mean, the standard deviation, and the other things that we talked about. This graph just takes a variable and it plots out different scores. We can think on a scale that goes from 0 to 6. And so what the number of people that score them. And the line indicates the mean. And so we can calculate the mean scores. And then, of course, people are going to score above and below that mean. The distance between the line and each of the dots indicates the deviation, so how much each individual score deviates from the average or the mean. So for instance, my average speed was 15 miles per hour, but at any point in time, I was probably going a little bit faster or a little bit slower or a lot faster or a lot slower, depending on all sorts of things. With correlations, we have not only one variable, but we have 2 variables. And so for each of those variables, we have a mean and we have a standard deviation or variance. And so we can think that we're going to put these 2 variables together. So for instance, on my ride, the average of the road, on average, we can think that the road was flat. I started and ended at the same place. But at any given time, I might have been going up with a positive gradient, or I was going down with a negative gradient. So with one variable, we indicate how much it varies around the mean. With the second variable, we can say how much do scores vary around that mean. So what we're doing here is we put them together. So in this case, I've layered these 2 variables together. Both of them have a mean, and both of them have scores that vary above and below that. When we look at it in this graph, we see very clearly that as one goes up, the other goes up as well. This brings us to one of the ways that we can calculate correlation. So here's the mathy part, but let's break this down. This is something called the covariance of two variables. Again, we have variable 1 and how it is varying with the other one, or covarying. So what we do is we take the deviation from one variable, the deviation from the second variable, and then divide that by the number of people that we have in our sample. I'll use an example of this in a moment that'll make this a little bit more clear. Now, this covariance is affected by the scaling that I have on the variables. So in the image I gave, we had a scale ranging from 0 to 6, and yet I said the correlation coefficient ranged from -1 to +1. So what we do is we take the covariance and we adjust it by the standard deviation in each of our variables, and that's going to give us our correlation. So this results in a formula that lets us calculate that. So let's try an example to make this a little bit more concrete. Here are a few sample scores. This is made up data, but we can think on our x variable is my speed at any given time, and my y variable is the gradient of the road, which could be flat, which would be 0, an incline would be positive, and a decline would be negative. And I'm just calling one x and one y. These could be interchangeable, which one I call x and y. Now, we're talking about pairs of scores, and so in each of these cases, we're looking at how the two variables fit together. So I was going 8 miles per hour when I was climbing a gradient of 7%. I was going 22 miles an hour when there was a -3 or a 3% decline going downhill. So what do I do to actually work through that kind of scary formula that I had? The first thing we want to do is calculate the mean and the standard deviation of each of these variables. Just like we did before, we're describing the mean and standard deviation of speed and the mean and standard deviation of gradient. Then what we're going to do is calculate how much each of those scores, working with the x variable and then the y variable, how much that score deviates from its respective mean. So in this case, a speed of 8 miles per hour is 6.67 miles per hour below the average of 14.67. And with gradient, the gradient of 3% is 1.17 above the mean of 1.83. So that gives me the deviation for each of my two variables. So now we want to put them together. And so we have the deviation in my x variable times the deviation in my y variable. I do that across each of my scores, and then looking back at this formula, what we want to do is add those up. So I take each of those co-deviation scores, sum them up, and I get negative 119.39. So now we need the next part of our formula. So we have negative 119.33 is my numerator. And then if we look at the denominator, we see we need the number of people that I have, not the number of scores because they're pairs, but the number of people, and then the standard deviation for each of my variables. So we can plug this into the formula, calculate this out, and we see a very, very strong negative correlation of r equals negative 0.97, such that as the gradient increases, my speed goes down. Thinking about bicycle riding, makes sense that it might be that way. Now, I've thrown a lot of numbers and formulas at you. Is your head spinning yet? Let's take a look at the second way to calculate this R correlation coefficient, known as the z-score approach. And this is actually an approach that makes more sense to me, just seems a little bit more straightforward. So lecture 10 talked about z-scores. A nice property of z-scores is that it lets us standardize any scale that we have. That is, it lets us take our scales, which can be on all sorts of different scalings, and puts them on a common metric that has a mean of 0 and a standard deviation of 1. And so what we're going to do is put together the z-score in my first variable with the z-score of the second one. The way to think of these two methods is the first one essentially calculates the covariance of two variables and then standardizes things. This one just standardizes each of my items and then puts them together. So let's use an example of this. The z formula that we talked about a few lectures ago, we just take each of the scores, subtract out the mean, and divide by the standard deviation. And so I can do this, again, working with each of my single variables. So I have, for my speed of 8, a z-score is going to be 8 minus 14.67 divided by the standard deviation of 5.02 is going to give me negative 1.33. And so we do that for each of my x scores, and then we do that for each of my y variables as well. For example, 0 gradient, so flat, 0 minus 1.83 divided by 3.48 is going to give me a z-score of negative 0.53. So then what we're going to do is we have a z-score for our x variable, a z-score for our y variable, and we're going to put those together. Again, we're looking at how the two variables vary together. And so I can take negative 1.33, multiply that times 1.48, gives me negative 1.97, and I can do that for each of my variables. And then again, I can add those up so I get kind of the summed deviation scores there. So here's the actual formula with R. So we take the sum of my z-scores added together and divide by the number of people. So again, going back to our table here, we have our sum there after we added those up was negative 5.85. And so we're just going to divide that by the number of people, which is 6, which gives me the same answer of R equals negative 0.97. To me, that formula just seems a little bit easier, but it just depends whether you want to calculate those z-scores or not. And then either way that we calculate it, we want to interpret the value, giving the direction and how large that is, such that we can make sense of it. So this is numbers, this is formulas. The best way to understand this is to practice it and play with it a little bit, entering some of these into the formulas, seeing where the numbers come from. I have added a practice sheet to my website where you can check that out. So today, we considered two different approaches for calculating the correlation coefficient, which is a statistic we use to indicate the extent to which two variables are related to one another. I'll note that in practice, oftentimes, especially as we get more and more data, we actually let computer programs calculate this for us. And that's pretty easy to do. But I think it's very important to understand where the numbers come from. I think once you actually work through this a little bit, it gives you a much better sense of what the computer is doing in the background to pop out numbers that we look at. And we use correlations a lot. Often when I describe a set of data, I'll give the descriptive statistics like we did before, and then I'll also include the correlations amongst all the variables. So it gives us an important tool for understanding both the individual variables and how they relate to one another. And then we'll build on this next time as we talk about regression. Thanks for listening. See you next time.